This is a collaboration between Moscow State University and Bristol, looking at porphyry copper deposits, and Oleg asked me if I would just provide a little bit of background, so that little bit at the end of my talk I didn't have time to deliver will serve as a useful introduction to the modelling that Oleg is going to talk about. So we concluded my talk with a concept of these deep magmatic reservoirs, or transcrustal magmatic mushes, in which a system composed of melts and crystals and gases exists over a big depth range through the crust, and the crystals, gas and melt, because they have very different physical properties including density, can move independently. And the example of Montserrat, Soufriere Hills volcano on Montserrat, serves as a useful illustration. And then in the second talk, Pavel Plechov showed some melt inclusions that show some very interesting features of the way in which different volatiles behave. And the point here is that resolution is very low, actually. The point here is that different volatile species degas from magmas at different pressures. And here are some experiments from a postdoc working with me did at Bristol, called Chris C. Lane, and it's not very clear here, but this is the normalized concentration, and that number there is 1. And this is the amount of different volatile species left in a melt, after a gas has exolved. And what we see, if we look at a species like sulfur, that says 500 megapascals, 5 kilobars, sulfur starts to degas around about 200 megapascals and is all gone when you get down to, this is 25 megapascals. On the other hand, chlorine is a rather resilient gas, if you like, has a much smaller partition coefficient into the fluid, and chlorine sticks around in the melt until very low pressures. That is not to say there's no chlorine in the gas, but chlorine has a much lower partition coefficient. And that's not a surprise if we look at melt inclusions. More terrible resolution, that says H2O there, 0 to 7 weight percent. These are melt inclusions from Mount St. Helens. If we look at the chlorine content, that says weight percent chlorine, that's about 0.1, 0.15, even 0.2 weight percent chlorine. They're not depleted in chlorine. On the other hand, sulfur, with a couple of rogues here, sulfur is down at concentrations, that says 0, that says 0.10. This is round about 50 parts per million, or close to the detection limit. So this is rather interesting because porphyry copper systems are associated with shallow, felsic intrusive rocks, or hyperbyssal rocks, and shallow felsic volcanic rocks have characteristics that are inconsistent with porphyry coppers because these kinds of magmas have lost all their sulfur. So a porphyry copper deposit is a sulfur anomaly, and yet the magmas that are associated with porphyries don't have any sulfur left. So you can see this equally in melt inclusions from Mount St. Helens. This says weight percent CaO, that says 3 down to 0. This is the weight percent of chlorine, 0%, that says 0.4%. And this is an index of differentiation. The magma is ascending and degassing mostly water, CO2, sulfur. Chlorine is going up slightly because of crystallization, and then it reaches a peak, and then chlorine starts to degas quite extensively, and chlorine drops. Here's the copper content. Copper goes up and then drops. And if we have a look at the behavior of copper and chlorine, they're very strongly correlated. And that's because, to a first order, chlorine and copper complex in fluids, although a question was asked earlier about how you get these very sulfur-rich fluids, and actually the ability of copper to complex in sulfur-rich fluids is not very well known. So one possibility then is that the sulfur is supplied from deep in the magmatic system, and the copper and the chlorine is concentrated shallow, and in this transcrustal magmatic mush we can take the sulfur from deep, add it to the copper chlorine-rich fluids, or brines if you like, shallow, combine them and make an ore deposit. So we set about testing that. The idea is that we can react sulfur-rich gas from deeper in the system to metal-bearing brine shallow in the system, and we can carry out reactions in which the copper becomes concentrated in brines that separate from long-lived felsic plutons at shallow level. The sulfur gases, whether they're SO2 or hydrogen sulfide, are supplied from deeper in the system, and the two react. Brine and fluid is fluid, there's brine to produce copper sulfides and HCl water. And a colleague of mine, when I first came up with this idea, said, John, you can write all the reactions you like. That doesn't mean to say they're ever going to happen. It's a bit like saying you can predict all the mineral species you like. It doesn't mean to say they're ever going to be stable. So we said, okay, well, we'll test this reaction. So we set about a couple of tests. I'll just show you these. These are experimental tests. And the first we called porphyry in a capsule. We set up a two-capsule system, a mafic magma here with a lot of sulfur and water, but no copper and no chlorine, underlying a felsic magma which contains copper and water and chlorine but no sulfur. And when we run the experiment, sulfurous gases, H2S and SO2, pour out of here and meet the brine. And we ran these experiments at 180 megapascals and 850 degrees. This is the mafic magma that's the source of the sulfur. Here's the felsic magma. We ran it, this is probably about an hour. Sulfur comes off here, meets the brine, precipitates, in this case, digenite. Very, very quick reaction. Then someone said, oh yeah, but you've got a lot of H2S in there. Magmatic gases are SO2. So we set up a different sort of experiment. In this case, we put the brine into a calcium-bearing host. It could be plagioclase. I could show you plagioclase experiments. These are with calcite. And now what we're going to do is we're going to use the disproportionation of SO2. So this time, here's the experiment. This is the top of the capsule. This would be calcite, and this is brine in between. We put sodium bisulfite in the bottom. We run the experiment. SO2 comes off. SO2 reacts with the brine. And here's the calcite. This is a backscatter image that says iron and copper. Lots of chalcopyrite. This is sulfur, calcium, lots of anhydrite. Basically, we've got this reaction, calcite plus SO2 plus brine makes sulfite and sulfate and carbon dioxide. And we often see this association of sulfide, bornite, chalcopyrite, and sulfate in ore deposits. So again, this reaction happens really, really quickly because hot SO2 is an incredibly reactive gas. There are hardly any stable sulfite minerals on Earth. So if you think of volcanoes bubbling their SO2 at high temperature through the crust, it's very, very reactive. Disproportionation to sulfide and sulfate happens very readily. What happened there? There we are. So we came up with a concept, and this is the concept that Oleg and Andre are setting about trying to test. And the idea is that we have two systems, a felsic magma that's evolved by differentiation. It's rich in chlorine, it's rich in copper, and it exalts a fluid that at low pressure becomes a brine. Again, the resolution's awful here, but little green dots here are brines stored in the upper levels of a magma system or even in the crust. This takes a long time because the volume of magma is relatively large. I'll put 100,000 years, that's a guess. This system is subject to very short-lived, intense pulses of sulfur degassing from deeper in our transcrustal magmatic mush. The sulfurous gases, mostly SO2, rise up, meet the brine, react like I showed you in the last experiment. Our proposal is that magmatism and ore formation are separated in time. The flow of brine and sulfur gas sources are decoupled. We don't just have to have magmatic brines. These could be sedimentary brines. They could be deep metamorphic fluids. It doesn't have to be magmatic. And the reaction process here may draw in brines from the surrounding area, and so the brine source may change during mineralization. So we put this idea to Oleg and Andre, and there's their disclaimer. And we said, can you model this?
Right. Okay, so I will start with a short disclaimer. Please don't shoot the piano player. He is doing the best he can. So I don't have a systematic geological background. My background is fluid mechanics. I'm not a stranger in geology department, though. Just in this room for many years for a few years with Pavel Plichov, we share a lecture course on physical volcanology, and it is multidisciplinary for the whole university. So, as I told, my background is fluid mechanics, and we will try to provide a tool to test the concept of the formation of the ore deposit. And all the question for the concept is for John. And I will start with, our modeling strategy is, first of all, we need to simulate the formation of a brine zone above the silicic magma chamber. And during the second episode is a flashing of sulfur-rich gas and precipitation of copper. So in order to do it, we need a simulator or software which should be able to simulate non-isothermal porous flows, supercritical conditions in a water NaCl system. We'll need to account for chemical reaction and complicated porosity permeability structure. So there are some available simulators, but none of them satisfy all the criteria. For example, very widely reached in industry is a TAF2 code, but it's only for subcritical conditions, so low temperatures, low pressures. Then hydrotherm go to supercritical, but it's only pure water, no NaCl. And recently in Zurich, they developed a code called CSMP++. It has most of the things except chemical reactions. My colleague from the Institute of Mechanics in Moscow State University, Andrei Afanasyev, developed a simulator which I am going to describe now that we are going to use in this project. But initially is a few slides for young students who are supposed to be in this room. So we are talking about porous media, and it is a rock matrix with some pore spaces, and the porosity is the ratio between the rock and between the whole volume and the volume of the pores. So porous media structure can be very complicated. So this image shows the location of the pores from a sample, and this image shows the propagation of some front of concentration of some elements during the flow. The law that describes propagation of fluid or gas in the porous media was discovered by Henry Darcy, and the experiment is very simple. You take a piece of porous media, you apply a pressure gradient, and then you measure discharge rate and or mass or volume of water that comes from the porous media at every 1 second. Then you divide it to this cross-section of the porous media, and you get filtration velocity or Darcy velocity. and it is proportional to the gradient of pressure, some coefficient that depends on the porosity, and reversely proportional to the viscosity of the fluid of gas. So water will go slower than the gas phase. Now there is a porosity permeability relation. It depends on the origin of the rock. For example, in volcanic products, explosive eruption pumices will stop be permeable at about 30% of bubbles. But if you have, for example, fractured lava dome materials, it is still porous when the volume fraction of bubbles is about 5%, because there is a fracture permeability there. So another fundamental law that is used for modeling is mass conservation, and it says that changes of mass in the particular volume of porous media is proportional to the fluxes of mass from outside of this volume, as simple as this. So Andrei developed a simulator. We call it MUFITS, Multi-Phase Filtration Transport Simulator, and it can be used in a wide range of applications: hydrothermal power generation, oil and gas production, or, for example, CO2 sequestration. And I will go briefly about the features of this simulator and on some applications. So it can read complicated geological structures, and it's compatible with industry standard in Eclipse software, which is widely used in oil industry. Oops. Okay, so it has multi-phase flows, including, and has different models, for example, water, CO2, black oil, which is used in oil industry, or other equations of state. It can be executed in multiple processors, and we use Lomonosov supercomputer here in Moscow to run simulations. And it has equation of state for a wide range of pressures and temperatures. Because there is a multi-phase flow, we need to have a more complicated system with two conservation of masses, for example, for pure water and pure CO2, conservation of energy with account for energy stored in the skeleton and energy stored by moving fluid, and in heat conduction and advective fluxes of energy. And we use Darcy law to simulate the motion of the media. One important thing is how to calculate physical properties in a wide range of pressures and temperature. And the code uses enthalpy and pressure as primary independent variables. And therefore, entropy can be introduced at thermodynamic potential here. And in an equilibrium, entropy will have maximum. And the code calculates maximum of entropy given total pressure, enthalpy, and composition of the fluid. So it can calculate up to 3 phases. It can be gas and 2 liquids, for example, for water and CO2 system. And here the diagram shows the equation of state. Here is enthalpy, pressure, and composition ratio of water to CO2, for example. And outside this green surface, there will be only 1 phase. Inside will be 2. Inside this red surface, there will be 3 phases. The code is quite accurate. The equation of state is quite accurate. So here is a comparison of the model prediction with some experiments, and usually within 5%, which is more than enough for geological applications, we can predict the properties of the media. MAFITs can handle complicated physical and logical models. So it contains an unstructured grid where nodes are connected by some graph, and parts of the graph can be not only pieces of porous media, but for example wells or pumps, and that will be described separately by some equations that will be incorporated in the solution matrix. The code was widely tested, and here is the test of CO2 injection scenario. There is a geological formation and a small air well that pumps CO2 into water-saturated system, and the model was compared with TAF2 and Eclipse, and give quite reasonable results on the area occupied by the injected CO2. Now, there was a simulation of a real CO2 sequestration project. It's in Northern Sea, Johnson Formation. They have oil which is very CO2 rich, and instead of paying large fees for polluting atmosphere, they pump CO2 back into water-saturated layer. And these conditions were simulated based on a parallel execution of this code. And here the plot shows the formation of a CO2 rich liquid, and of course there is a complicated topography of the layer. So in the upper parts of the layer CO2 is concentrated, but within 2,000 years it will start to leak from the formation. That's what we've shown. Another application is simulation of multi-phase flows in hydrothermal systems. We used with Italian volcanologists examples of Campi-Flegrei caldera, and this is the geological model with a complicated porosity permeability structure. This graph shows the evolution of temperature at some depths due to convection in the hydrothermal system. And there is a good comparison with, there are several wells here, and there are temperature and water density measurements in these wells. There is no other simulator that can model as deep as 8 kilometers like we do here, because TAF2 is only capable for last couple of kilometers because it uses subcritical equations of state. Another interesting application we did with Bristol people is when you have a kimberlitic eruption and you form a kimberlitic pipe, then it starts to cool by external water influx into the system. And there will be a mineral reaction. One, the most important, is transition of olivine to serpentinite. And it requires the presence of water, and it increases dramatically the volume because the density of serpentinite is smaller than the density of olivine, so there will be pore blockage, and which will reduce H2O flux. Also, this reaction is non-isothermal, and there will be quite significant heating due to the reaction. So we introduce the simulation domain. This will be an area occupied by high porosity kimberlite, and there will be two layers, more porous and less porous of the country rocks that are initially water saturated. Kimberlite is saturated by air because it was a production during explosive eruption. And here we introduce some kinetics of serpentinization that accounts for non-equilibrium process. And there will be a complicated evolution of the system because in order to have serpentinite, we need particular temperature conditions and presence of water. So here this plot shows the degree of serpentinization during the kimberlitic pipe cooling, and you can see that you can that this can result in a complicated structure where in some parts of the pipe fresh olivine was preserved because the water wasn't able to come into the system before it cools down significantly. Here the plot shows the influence of the pipe permeability on the serpentinite distribution, and if the pipe is not very permeable, only in the outer part of the pipe you will have a formation of serpentinite layer, and inside the pipe you will have fresh olivine. And if the pipe is very permeable, only the top surface of the pipe will cool quickly enough to preserve fresh olivine. Some other tests relate to oil production, and this is a test from the Society of Petroleum Engineers, where you have production wells, and in some wells pump water, and there is a good agreement between the predictions of the code and the simulations. And also the simulator was tested for real oil deposit production, and it gave a very comparable result to industry-used simulators. So in order to use MAFIDS for this project, we need to incorporate NaCl equation of state, first of all, and then we need to look at tracer transport like sulfur, copper, and other things, and we need to introduce chemical reactions in brine system. So this work now is supported by the Russian Science Foundation, and we've just started this project, so hopefully within a year we will have some results to show. But at this time, those who are interested in this simulator can go to the website. There are executables and documentation. Also, Andrei is doing training courses, and in Bristol University and in Germany, this simulator is already quite widely used. So I'm happy to answer the questions if there are any. Yes?
With respect to the kimberlite pipe modeling, it's been talked about how Udachnaya is so fresh. And your parameters were suggesting that permeability was a key control.
Yeah.
Does that mean, for instance, that Udachnaya has particularly low permeability? Is that the explanation for why that pipe is so much fresher?
I only show the influence of permeabilities, much wider range of conditions where you can have fresh olivine preserved. For example, it strongly depends on the proportion between olivine and other minerals. If olivine is not 100% of the initial mineral assemblage, then you will not close the pores because olivine will react and form serpentinite. It will expand, block some pores, but because olivine is not 100% there, or the proportion of the melt was high enough, then it will not block. So there is a paper with Steve Sparks, which you can refer to. But of course, permeability has a key role there.
I have a related question. Have you ever tested those different predictions on different kimberlite pipes? One of them, for example, showed two different serpentinized layers separated.
Mm-hmm.
Do any kimberlite pipes look like that?
Yeah, actually, Steve and John Schumacher had a geological comparison part in this paper, so we can look there. Yes. it is introduced as relative permeability curves. So depending on the rock, yes, you can use different relative permeability curves, and that's how this thing is usually modeled.
Is there any information on magnetic behavior
For kimberlites,
for example,
for kimberlites as well.
magnetic chloride?
For oil industry, definitely they provide. This is one of the tests that is provided for oil.
What shows the great difference between the behavior of oil and light?
Sure, but oil water system they do experiments for water for oil also.
Could you extend usage of your methods to melt, to fluxing melt?
Right. In principle, yes, because the simulator is made of two parts. One part is sort of geological and fluid mechanics, and the other one is equation of state. So in principle, yeah, if you introduce liquid with a different viscosity, you can. But I think important for melt transport is the compaction. In our case, the skeleton is inert. So yeah, but there are papers by Yuri Podlatchikov, for example, which they do proper modeling for melt extraction, I suppose.
When you say the framework's inert, so you can't have any reactions?
No, I mean that it is not deformable.
It's not deformed. Okay.
Yeah, that was not correct.
I wasn't quite sure how you do serpentinization with the inert matrix.
No.
Okay, any more questions before we move on? Okay, well, thank you, Oleg. So, Sasha, we're a little bit ahead of schedule, so no problem. That's a problem, okay. It gives us time to get set up.
Yeah, maybe I will be a little bit slow. You can talk very, exactly.
Yeah.
What I
Mine was HTML, yeah. Okay, great. Okay, so our final talk before lunch is by Sasha Borisov, and he will talk to us about multivalent elements in magmatic melts, with special emphasis on the ferric-ferrous ratio.
Okay, ladies and gentlemen, dear colleagues, in present lecture I'm going to talk about multivalent elements. It's very important, or rather complicated, but interesting problem. Interesting and important for geochemistry, chemistry, and petrology. Actually, I will show you three redox pairs. I will start with europium 3 plus 2 plus. It will be just an example to demonstrate how important it is. Then I will show you titanium 4 plus 3 plus ratio, because here I use a relatively tricky technique to estimate this ratio in silicate melt in equilibrium with rutile. And of course, in more detail, I will discuss ferric-ferrous ratio, the most important for earth processes. Let's start with the beginning. If you put in silicate melt at not very reducing condition some iron oxide, it will divide it between two species, ferric and ferrous. They coexist, of course, but nevertheless in oxidizing region ferric will prevail, and in reducing ferrous will prevail. The same happened with titanium. If you put titanium, it will also divide it on two species, 4 plus and 2 plus, and again in oxidizing you will find titanium 4 plus, in reducing titanium 3 plus. I should say that, of course, reducing and oxidizing conditions are very different for these different pairs. For example, at QFM minus 2, most of your iron already reduced form, ferrous, but still the most titanium is still in titanium 4 plus form, so it's oxidized, yeah? There's some more complicated cases like chromium 6 plus, 3 plus, 2 plus, or even tetrate, vanadium 5, 4, 3, and 2 plus. Okay, and in material science, people add you a lot of equilibrium. Good. Let's start with europium. You all, of course, know about so-called europium anomaly. It could be positive, it could be negative. And here's an example of negative europium anomaly. It's rare earth element content in lunar mare basalts, normalized to Ci hydrides, and it is assumed to characterize plagioclase fractionation from the source at reducing condition. So, how people know that conditions were reduced? Many years ago, Drake and Whale make very interesting and precise experiments. They measure partition coefficients between plagioclase and silicate melt for the spectrum of rare earth elements. And when they use air condition, it was a relatively smooth curve, as expected from lanthan to lutetium. But when they started to decrease oxygen fugacy, they found the increase of partition coefficient for europium. And at very reducing condition, it's minus 12.5, it's about iron was tight minus 2. They found that partition coefficient cross very important boundary unit. So before it was incompatible behavior, now it's compatible behavior. And the reason is that most of these elements have only one valence, but europium, in addition to europium 3 plus, have also europium 2 plus valence, and as a result, the low oxygen fugacy, the higher portion of europium 2 plus and europium 2 plus like to go in the structure of plagioclase. So from this example, you can see that it's very important to understand the ratio if we are talking about multivalent elements. In geochemical literature, in our science, people prefer to manipulate with a formal oxide ratio like iron O 1.5 to iron O and so on. And the reaction, redox reaction can be written in the form 1. It's easy to demonstrate that the ratio is a linear function, log ratio is a linear function of log oxygen fugacy and a reciprocal temperature for the same melt composition. Material scientists prefer a little bit a rather reaction. They like to write the ratio like iron 3 plus to iron 2 plus, titanium 4 to titanium 3, and so on. And reaction change to 1A reaction. But immediately appears a problem. You can see the more basicity of silicate melt, the higher activity of free oxygen, and we should move our reaction to the left. So we have to stabilize reduced form. But from experiments, we know that behavior is completely different. Here's a result from Paul and Douglas. And you can see that for these binaries, potassium oxide, sodium, and lithium oxide, there's a different behavior. The higher amount of alkalis, the higher ratio ferric to ferrous. This problem was, we can say that it was solved. Holquist suggested that we cannot simply write iron 3 plus, we should, or at least we can use some kind of oxyanion, and in this case everything working fine. The higher basicity, the higher activity of oxygen, the more the reaction will move to the right, so we can stabilize iron 3 plus as expected. Okay. in any doesn't matter which reaction we use, 1, 1A, and so on, the reaction 2 is valid. The ratio, the redox ratio, the log of redox ratio for the same melt composition is a linear function of log oxygen fugacity and reciprocal temperature. And this partition, this coefficient is very interesting, very important. Actually, theoretical K is n divided 4, where n is a number of electron in redox exchange reaction. Yeah. So for one electron exchange reaction, like our ferric ferrous, the slope is 1/4. For such reaction like tin 4 plus 2, 2 plus, it's already 1/5. And for relatively exotic for earth science, but for glass industry, it's not so exotic. Chromium 6 plus to 3 plus, the slope will be much higher. And in this plus, I especially calculated how quickly will increase the portion of reduced species when we decrease oxygen fugacity. And I started with the same for all pairs. I started with the same oxygen fugacity where exactly 10% is reduced form. Yeah, you can see that actually our ferric ferrous ratio will increase relatively slower, so it's easy to analyze. It's much bigger, will increase, let's say, tin 4 plus 3 plus, and much more quickly our ratio is 6 plus to 3 plus. And of course, the extreme example is sulfide sulfide. You can see that it's 8 electron exchange, yeah, so the slope is very high. So in reducing condition, most of your species will be sulfide as 2 minus. But let's say you reduce oxygen fugacity oil for 1 order of magnitude, and most of your species will be sulfate. Okay. Now let's discuss titanium 4 plus 3 plus ratio. Many years ago, I studied the effect of titanium on palladium, melts, and you can see that the part of my palladium group. So I worked on very reducing condition. I worked on very titanium-rich system where rutile was accessible. So it was almost mostly nuclear use rutile. And you know, I walk along this temperature, and when I reach very reducing condition, immediately appears some strange phase. Yeah, some strange phase. We studied it and found that it's so-called Karai. It was very funny story with this Karai. When I published the paper, I immediately obtained a very angry mail from one scientist. He wrote me, it would be so cool, but I will never cite it because you use a wrong term. You shouldn't say Karai, you should say pseudochloride. I answered him, okay, it's perhaps your games, but you know, it's some kind of byproduct. And I found that many people in literature use the term Karai, and he answered me again. Say, oh, that's it. But it doesn't matter if it's Karai, pseudochloride. We can say that iron-free analog of so-called armalcolite. Armalcolite is a real phase found in the moon rock and named in honor of this Tim Armstrong, Aldrin, and Collins. And you can see that this mineral species, my mineral species, armalcolite, contained a lot of titanium 3 plus. And perhaps we can assume that if we have a phase with titanium 3 plus, perhaps in our melt also there's a lot of titanium. And can we try to estimate how much titanium 3 plus we have in our selected melts? Okay, we will discuss only rutile situated melts where there's no chloride, so there's no change in composition. It's on. You will see. Okay. So first of all, I study very precisely rutile solubility at that condition, and so I can say exactly that at 1300 the solubility is 25.3% of titanium oxide. And here you can see the level of rutile solubility at that condition. But at reducing condition, solubility is high. The low is the high solubility of rutile.
Базальте в чем?
It's not surprising because we have in addition to titanium 2+, which is responsible for our rutile, we have also rutile 3+. So we can take this excess to convert it in titanium 2+ and to calculate the ratio. And this equation is shown here, and what is important, until now there was no assumption about the slope, but you can see that slope is extremely close to our theoretical value for 1 micron exchange, 0.25. Yeah? So, which means that this approach behaves as right. Yeah? If we use this equation, we can calculate that we have relatively maybe high, maybe low, but at least up to 6% of titanium 3+ in total titanium. When we calculate it as more reducing condition, let's say at iron side -1, lunar condition, we can say it should be about 8% of titanium 3+ in total titanium. Unfortunately, or we can say fortunately, there's other people who study titanium, and you can see that Schreiber, it's a famous scientist in our business. He studied two systems and found that the content of titanium 3+ much lower in total titanium, which means that we cannot use my data, and perhaps we shouldn't use this data. We should understand how melt composition, or maybe also how total titanium content affects titanium 3+, 4+ ratio with unfortunately, there is some limitation. First of all, it's an analytical problem. You cannot use iron-bearing melts or iron-bearing slags. But what is more important, the so-called mutual interaction of two redox pairs. So I surely can say if you have something in silicate melt, it's not necessary that you will have the same in conch glasses. So you cannot use in any case iron containing melts here. It was I found in all literature this exists, including slag study, all composition with measured titanium 3+, 4+. You can find some detail in my paper. I just show you the last equation. So you can see the ratio of titanium 3+, 4+ is a linear function for portion of the state. Assume here ideal slope. It's a function of a reciprocal temperature and composition. In my case, I use only modified also network form elements, silica, alumina, and titanium. And now we can estimate, for example, trivalent titanium monomers. For this reason, I use crystalline glasses. Still, I don't believe that it's the best candidates for the primary melts. There's some titanium poor variety, so-called green glasses. There's, of course, titanium rich melts, so-called orange glasses. And if we use these melts, we can estimate that at 1300 degrees, for example, in wire temperature to humidity, a portion of titanium 3+ and total titanium is relatively low. It's always below the 1 sample. If, however, we fix fugacity and change temperature, we can see that at high temperature we can actually really have a condition when the portion of titanium is getting really high. And it's not surprising that you can see again that slope is here 33,000. I can remind you that for ferrous ratio in equation you have about 5,000. And here 33,000, which means that it's very sensitive to the temperature. And now in the connection of this problem, I want to show you something. 2 slides. A danger of using relative oxygen fugacity in all necessary and unnecessary cases. A lot of people use a relative fugacity because it's very convenient. You shouldn't worry about temperature. Just say it's perfect minus 2 or iron is positive. So I show you 2 examples from plasma-chemistry. If you decided to plot partition coefficient for some normal metal like iron, cobalt, nickel between metallic phases and silicate phases, you will find that this isoplet are more or less parallel to iron oxide buffer condition. So it's not a problem to use here relative oxygen fugacity. Because, for example, for iron oxide -2, it's always the same partition coefficient. Yeah, it's convenient, you can use it. But it's not the case for some elements. Many years I worked with noble metal, and I can tell you that noble metal solubility is always anomalous. And here's an example for palladium solubility. And you can see that they simply not parallel, they cross this iron oxide buffer. And if we, for example, decided to have a look on 1 ppb palladium solubility in silicate melts, in equilibrium with metallic palladium, of course, yeah, you can see that at low temperature it's iron oxide -2, but for much higher temperature it's already iron oxide here +2 or here -2.5, which means that if we decided to use relative fugacity, we would still. Okay. And now we go to ferric ferrous ratio, the most important ratio on Earth. When I talk about ferric ferrous, I always like to show this stone because there's a beginning of this wall, but there's no end. And after us, ferric ferrous is so important that after us, the new generation will try to put some new stone on the top of this. And the first stone was based as early as in 1948. Kennedy, at least in our science, because people in material science would also worry about ferric. But in our science, Kennedy was the first who told us that in basalt there's no simply iron oxide. There's a ferric, there's a ferrous, and we should worry about the ratio because at different temperature, different oxygen fugacity, the ratio changed dramatically. Of course, the highest, heaviest, the biggest stone was based by Prямая. Yeah? All of you know important and really first working equation to connect ferric ferrous with oxygen fugacity, with temperature, and with the melting position, written in this relatively simple form. It's DIXI, some DIXI, where XI are more portion of component and DI some experimentally found coefficients. Okay, being a young scientist, I also work with ferric ferrous, but then I go in another areas, and a few years ago I go back into this business, and I will show you why. Again, this is the second condition, it's the first one, and now we have already 9. It was 8 when I started preparing my lecture, but months ago Putirka published a new one, so it's 9 already. Many years ago, Nikolai made a big job. He decided to check and compare some equation existing in that time. Yeah? And he demonstrated that all of these 6 equations more or less, maybe the missing equation was slightly worse and my equation was slightly better, but nevertheless, they are more or less similar. They predict experimental data set is more or less the same error. On result on the Z decomposition. But he demonstrated also that no one describes the segment with reasonable accuracy. And I can add to you that no one was calibrated for either American map. You all know that it was basalt, and people don't like to work with parametric map because you need a high leverage. Then, all equations give different TFO2 trends for the melt during fraction. I will not show you, but just different trends. And at last, most of such equations ignore the effect of titanium and phosphorus sulfuric ferrous ratio. Okay, the amount of phosphorus is not very high, but I showed you lunar rocks, for example, with up to 15% of titanium oxide. So it's why we should ignore the titanium. And here's a couple of figures from Kutirka, just to show you that that's a problem. You can see the ferric ferrous at different temperature, for example, at VFM plus 2. You can see the difference. Now, I don't want to say this equation is right, that equation is wrong. They more or less, more or less similar can describe the experimental data set, but you can see the difference. And this difference will convert it in huge difference for AD. So we really need to think about ferrous again. And I would say that it's time to generate an ideal equation. What is ideal in my sense? It must be applicable to Celestica ultramafic melts. It must reproduce TFO2 trends in closed system during crystal differentiation. It must precisely describe the effect of all melt component on ferric ferrous, including titanium, of course, and it's better also phosphorus. Okay? And now a very small excursus in thermodynamics of solid solution and behavior. Okay, when sex adjusted his equation, he wrote that equation, though reminiscent of thermodynamic form, should not be confused with it. It's right. But nevertheless, we can say that we have this term somewhere similar to the ratio of activity coefficient of ferrous. And in principle, we can play a little bit with thermodynamics. I will skip it, and just the conclusion that sex model assumes that silicate melt are not more complex than symmetric regular solution. Obviously not more complex. But we know that if we decided to use asymmetric regular solution, so in addition to this term, we should add some this term, that term. So, and this to describe a component melt, one will need minimum 36 terms. If you play with linear regression, you understand me that it's practically impossible. It's possible to obtain these terms, but you shouldn't believe them completely. So instead, we propose to use simple DIXI expression with the most component, which I call not critical, but with a few additional terms for some component which I call critical. And of course, such critical components need to be identified on the basis of experimental study. You cannot say, perhaps this is critical, perhaps it's not critical. Yeah? You should make experiment to understand something. And I show you a few examples, not all of course, because now I studied all components, and I will show you titanium. The effect of titanium, it's not critical. I will show you the effect of alumina and magnesium. They are also critical components. And I will show you the effect of potassium, the most exciting component. You will see. You will see. Okay. So I like to work, and I also work with anodized dioxide with different composition. Actually, when I started with chemistry, I used this one. So before typically this is half of the work. But now it was 10% of iron oxide, so it's a real synthetic resolve. Okay. And sometimes I add silica, sometimes not, so I have a base composition and I have silicium composition. And both these compositions were enriched in a variable amount of titanium, aluminum, magnesium oxide, or potassium oxide. Yeah? And for potassium experiment, I also use some low-depth composition in silica, aluminum, magnesium system, which is calcium. I will show why it's important to use also calcium-free component. All experiments were done at air condition. Typically, the whole series was in a single run, so we can avoid even small error in temperature regulation. But what is more important that all samples of series were analyzed in a single analytical session. So we want to avoid even small analytical problem. Because we want to see sometimes very small effect of melting transition. And here's the effect of equilibration time. You can see that at high temperature, 1500 degrees, 2 hours is sufficient to reach equilibrium not only in basic silicate melts, but also in silicic. In silicic, it's typically very difficult to reach equilibrium. So on this reason, I like to work at very high temperature. And here's the effect of titanium on ferric ferrous ratio. And you can see that both in basic melt and in silicic melt, if you add titanium oxide, you decrease ferric ferrous ratio. And you can see it here, for example, yeah? Sometimes really effect is small. It's for titanium free, it's 1.9, for titanium rich, 1.6. So it's very, very important to have a minimum error. Okay, and all these experiments, both silicic and basic, can be described as a simple equation if we use a set model. So TiXi, in our case, silica is variable and titanium is variable. Yeah? And you can see that all these experiments can be described with very high R squared. So titanium oxide is not critical. But it's not the case for other compounds. For example, you can see here magnesium, effect of magnesium. In silicic melt, you can add a lot of magnesium from 5 to 21 with 8% and nothing changed in respect to ferrous. But if you add magnesium in basic melt, you can really see the increase of ferrous as expected, because magnesium is a weak, but nevertheless it's network modifier. The same is alumina. Alumina addition decrease your ferric ferrous at fixed temperature oxygen, but you can see the difference effect. In silicic, it's very strong, and in basic, it's much more weaker. We just can try again the sex model. So two variables, silica and alumina. So we obtain some equation which is much worse, yeah, ask when. But what is more important that if we plot our calculated trend, they systematically overestimate the effect of alumina in basic melt and they additionally systematically underestimate the effect of alumina in silicon. But again, we want to produce very precise equation in the future. So I tried to play, and I found that one small term, additional term, absolutely sufficient to describe this system. Yeah? So it's R squared gets very good on 91, and you can see that calculated ferrous ratio. Indeed, according to experimental experiments, differ in basic and silicon. Okay, now we go to the potassium, the most exciting component. It's hot data obtained 2 months ago, somewhere, when I was last time in Hanover. Again, you know, all my life I worked at 1 atmosphere. I always use a loop technique, radium, plating, gas. And it is a fantastic technique. It was always convenient, but unfortunately there's a so-called it's sodium and potassium evaporation from the system. This all consists of all people know. So here's again very extreme example. Many years ago I studied the effect of sodium on iron. So I work with iron glue. It is very recent condition. I studied -1.2. And you can see I started with 17% sodium in my initial melt. In 30 minutes it was only 4%. In 1 hour it was 1%. And in 4 hours it was nothing. All sodium was evaporated. Okay, again, it's extreme example. I work with their condition. Of course, it's much lower losses of sodium or potassium, but nevertheless they are. And let us understand how to convert experimental condition voltage into voltage. Is it possible? Or not? It's possible. So we know that 2 hours is sufficient to reach equilibrium. So the shortest experiment at 1500 degrees should last 2 hours. Let us add additional longer experiment. We know that we will lost more potassium. But this way we can produce sample with different amount of potassium, so we don't need to mix addition. We just put it in the furnace, and instead of 2 hours, we put it there 4 and 6 hours. It's very good. And what is more important, we need to demonstrate or not to demonstrate that the process of ferrous equilibration is faster than alkaline flow. And here you can see here all my experiments made with potassium containing sample. You can see that indeed, even at their conditions there's sometimes a huge loss of potassium. But you can also see that sometimes there's a gain. There's a gain. So we started with potassium-free sample, and in this case we have already 4% of potassium in our silicate glass. It's not surprising if you remember that there's evaporation. If you put your, let's say, sodium-free sample between sodium-rich sample, there's the common cloud of potassium. There's some partial pressure of potassium oxide. So it's understandable why some potassium-free melt can accept some potassium. Okay. But what you can see here from DAFSK sample, there's one with significant loss here. There's this moderate loss, and loss 15%. There's a sample also with a but they are all located on very precisely determine line, which means that indeed periodic vibration in our case faster than loss of gain of AC. And here's a both here this one and another one, and you can see we can calculate and say that effect of potassium increase, very seriously increase ferric ferrous ratio at fixed temperature and oxygen. You guessed it. This one paper you can find tolerable, perhaps was the only one who tried with a natural basalt and enrich it with different heterogenic oxide. And here in one case is potassium also. Of course, Asqua is much poorer than in my case, but nevertheless we can see that again here for natural basalt, for lower temperature relative to minus, and for low oxygen fugacity, the slope is more or less similar, which means that indeed at any temperature, at any oxygen fugacity, if you fix this parameter and increase the potassium in our silicate melt, we can dramatically increase ferric ferrous ratio. And now go to this calcium-free melts. Yeah, I told you that it's very important because for this calcium-free we can strongly say here we have meta-aluminous melt where aluminum content, atomic content higher than potassium, and here we have a pyrrolocalline melts where amount of potassium is higher than aluminum. And we can see that all these samples located in the same line without any, any break. Yeah, nothing happened when we cross this boundary. I want to emphasize it because now we will discuss one very old conception. In 1991, Dickinson and Hess made experiments in silica alumina potassium system with 2% required oxide. It was also air conditioned, it was also relatively high temperature for the body. And they found that here in metaluminum there's one flow, but in pyrrolocalline there's perhaps another flow. And they wrote the discontinuous redox behavior associated with the composition near KO2 starch equal 0.5 clearly shows the abrupt change in melt structure. I should say that this conclusion moved from one paper to another paper to another paper, and actually I was also one of people who cited this conclusion. So I will show that maybe they are right. Now, you can see that it's written slightly different way. It's a ratio of ferrous to total iron. Let us convert this value for what I showed you before. Ferric ferrous. Here we are. What we can say now? We can say that in meta-aluminous melt, where the ratio is not very high, where precision perhaps is relatively reasonable, there's a real effect when we increase potassium content, we increase ferric ferrous as it's. But in pyrrolocalline area, we can see nothing. You can see the scatter. We can say perhaps the ratio is so high and the error of determination is so high that the scatter conflate all possible effects. So now we can say that there's no discontinuous redox period, and perhaps there's no abrupt change in melt structure, at least if you based on the ferric ferrous. Yeah, some people working with some physical technique, atmospheric spectrometry, maybe they say, okay, it should be, but we cannot say based only on ferric ferrous ratio. Up to now, I collected already actually huge amount of data. So unpublished data and this unpublished data, where I started from calcium, sodium, and potassium. Now it's 150. One experimental glass. From ultra basic to silicic, there is titanium rich, phosphorus rich, alumina rich, and now alkali rich varieties. And all these glasses can be precisely described with a single equation if we add only two additional terms. This one to describe silica-alumina interaction and this one to describe silica-magnesium interaction. You can see that as well as very. So, main conclusion. Silicate melt are more complex than symmetric reactive solution. Addition of two terms in empirical equation allows to precisely describe all our experimental compositions. So the work on creation, an ideal equation, moves forward. However, there is some problem which people should solve. I don't say that I will be the guy who can solve this problem. Maybe again, next generation. We need to compare the effect of different components of ferrous ratio in oxidized ferrous reducing condition. Of course, we can ignore it and we can assume that it's the same, but it would be better if we can check it. We need to be sure that our coefficient and log oxygen density similar to different melt composition. There is some data that perhaps would be some effect of melt composition. But again, we can assume that it's the same, but it's better to check. And at last, it's very difficult, but we need to understand how to make into account what's called interlaboratory error. And only then the work on application of ideal equation will be finished. And now the real conclusion. Ferric ferrous in silicate melt at constant TF condition increase with increasing magnesium, calcium, sodium, and potassium, and effect of net modifier of ferric decrease in the role. Potassium is the most strong, sodium is less, then calcium, and then magnesium, which is critical, so it's different for different composition. The same with network of Hume. They decrease ferric ferrous, the strongest player is phosphorus, then silica, more or less similar to titanium, and then alumina. And present data do not support the established opinion that ferric ferrous behavior must be different in meta-aluminous and pure alkali metals. Thank you for your attention.
To ask the very obvious question.
What I would like to ask.
Ask the very obvious question.
Only.
It's a glaring question, anyway. Go on.
Really. I would like to ask you, in alkaline melts, a lot of uranium, you know, we have a big deposit there. And what do you think about uranium-4, uranium-6 ratio? Because not today, but some days, some years ago, maybe 2 years ago, you presented very interesting results that comparison oxygen fugacity in those pairs. And can you tell about 4, 6 uranium? That's very important for us.
I just came to tell you that there's a very old paper already. I told you about Schreiber, who is an expert, and he specially measures uranium species at different oxygen fugacity. So you can have a look and you will understand something.
So you don't remember?
No, I don't remember. Because actually it's 3 valencies. So it's you cannot say it's 3 plus 5.
Just for us interesting, because John Blandi, he noticed that in our alkaline rocks, in peralkaline rocks, there is no europium anomaly because of high alkalinity. Yeah. But maybe it also can tell us about this pair, because I don't know which is oxygen fugacity less or more as compared with
I don't remember, but it's
europium.
obviously published.
Okay, good.
You talked about the absence of any breakup in the between metaluminous and peralkaline systems, but there is a big gap of experimental data. And
I agree, but because it's a real experiment, so when you start experiment, you never know exactly where you finish it. So how it will be, how much will it gain or lost. And typically, it's some experimental problem because I need to make it quickly during 3 months. Experiments, measures. Of course, you can remeasure again and again and at some points, but I am absolutely sure because I have very similar to sodium. And for sodium, it's also there is no
Don't you think that your experience and your results give rise to the conclusion that there is a need now to go from simple oxides, not activity models, to another set of models, I mean ionic models, polymerization models, and so on?
No, if in principle you can produce a model which can be applied to the very complex composition, well, it's wonderful, but perhaps, and you know it's better that, I guess, you know, we can compare, there are some so-called thermochemical equation, Moretti, and Moretti gave the Boston. If you use very simple ones, just completely, just use multiple linear regression to a lot of experiments, you may obtain better equation, which means that now we can go produce something very good. Maybe it's the future.
Everything in the future.
Okay, well, I'll ask the very obvious question. The most important magmatic component, water. You can't put water in one atmosphere. What about water?
Yes.
Yeah, you told me once. Yeah.
We talked about this. I have some data of my own that show that the effect of water is enormous. Probably because in that list of things that matter,
The only what I can tell you is that perhaps we can think about experiment which should be done where there's no comparison with calculation. Because if you start to, and perhaps you use also silicic one, yeah?
No, basaltic.
Basaltic, but nevertheless, yeah, okay, made first experiment at 1 atmosphere, different temperature, ocean fugacity shows that one of these 9 equations absolutely precisely can describe you, and then go to high pressure experiment with
Well, I think I like your idea of using half the basalt and just adding water systematically.
Yeah.
Use plastic capsules, no, well, actually probably not plastic, but use, we'd have to use capsules where we didn't lose any iron, but maybe we could do them at low enough temperature to use gold.
Gold, no. You should go in very low temperature and will never reach it.
Well, I wonder if you put 20% water in those things.
No, I mean if your temperature below 1000, you will never reach it.
Oh, well, if you've got water, that speeds up the diffusion rate.
Maybe.
The diffusion time is a function of...
Okay, if you demonstrate, but what is better? Not compare the dry and water rich. Maybe it's better to produce a sample with some different amount of water, let's say 5. And if you really can see some trend, you can say yes.
I'll show you at lunchtime, I can see a trend. Okay. All right, well, thank you. Let's thank the board speakers.
Okay, I have an announcement about lunch. We have 6 cafes inside the building, and 2 on the second floor, and 4 on the first floor. Sorry, in the ground floor. And if somebody don't know the way, ask the organizer.
Павел, я сейчас сматываю. Должны уехать, потому что надо делать подъезд. Еще Википедию надо добрать, там выше копировать. Ты оставайся начальником, значит, я попросила Сашу Борисовну быть кабинером до конца. А потом ты объяви, что значит те, кто имеет тикеты, должны идти, да, должны идти на банкет, ладно? На! Пойдем. Видишь?